In this lecture, we're going to implement a few different methods. The first method we are going to implement is going to be search. So since we created our iterator, we could very easily use it to search for the value that we want to see if it is in our tree or not. But I'm going to take a different approach and not use our iterator for searching our tree. If you want, it would be good practice for you to implement another search method that does use our iterator, but you don't have to. But again, it will be good practice. So what we're going to do is we're going to create our search function method, and it's going to need our value passed in. And what we want to do is we're going to return a Boolean if it exists or not. So what we want to do is we want to use our compare and ordering in order to kind of navigate through our tree. So up here we'll bring ordering into scope. We'll say compare and ordering. And now back in our search method we can say match and self.value, and we are going to say some key, and then inside this code block we are going to match on our key and compare it to our value. So there are three things that we can have here: equal, greater, and less. So we'll start with the easy one, which is equal. So this means that our key equals the value, therefore it is in the tree. So key equals value. So if it's in the tree, then we want to return true. Otherwise, we can have greater, and this means that our key is greater than the value, which means that we need to go to the left because we're looking for a key that is now going to be less than the value. So we will say self.left, and we will say some node. We will say node.search, so call our search again on our value. And then if nothing comes back, then we know the value is not in the tree, so we return false. So now, and I see I have a typo here, so we will go ahead and fix that. So now we have ordering, and our last one is less than. So in here, this means our key is less than the value, and so this means we need to go to the right. So we will say self.right, and it'll be the same as above. So we'll have node.search on our value. Otherwise, if nothing comes back, then we know it's not in the tree, so we return false. And then to do our catch-all, we return false here as well to close off this match statement. So let's just make sure that the syntax is right. So let's do a cargo build, and there we go. Let's do another cargo build. Alright, so syntax is right here. So search seems to be working fine, so we'll leave it as is for now, and then we'll implement our test cases for all of the methods we're creating at the end of this lecture. So now that we have search done, let's implement a method called minimum, and minimum is going to return the smallest value in the tree. So we will say pub effin minimum, and we will need our self, and we have option with a reference to t. So in here we have our match self.left because we want the minimum, so we know that we have to go to the left, and we will say some node dot minimum because we want to get the minimum node, and we will say none if nothing is less than self dot value as ref. So once we get the minimum value, then nothing will be less than our self.left. So we want to return our value as a reference. So if we have a minimum, naturally we need to have a maximum, and this is going to return the maximum value in the tree. So we have self, we're going to return our option with a reference to our value, and it'll be the same thing, match and self.right, some node, and we want node dot maximum. Once we get the maximum, we will have none, and we want to return self value dot as ref. Alright, so we have minimum and maximum. Again, we will test these once we are done implementing our methods, just to ensure that they work. So the next method we want to implement is called floor. And floor is going to return the largest value in the tree smaller than the value parameter that we pass in. So we will say pub effin floor, and we know that we need our self, but this one is going to take a reference to a t-type called value, and we will say option, and we will return a reference to our value. So inside of floor, we need to do a couple of things. The first thing is we need to match on our value, and then for some key, add in a code block, and then for some key we want to match in on key.compare. So this should look kind of familiar since we just did this in our search method. And now we want to do ordering greater. So again, this means that the key is greater than the value. So we're on the right, so we're going to go to the right. Match self.right. Or no, excuse me, we want to go to the left, because in this case we want the largest value in the tree smaller than. So we want to go to the left. So now that we're going to the left, we will say some node dot floor on the value, and then none. So if there is no value that is less than this value, then we return none. Okay, so now we have greater done. So now we want to do our less than. So we have ordering less, and so this means that the key is less than the value, which means in this case we want to go to the right because we're looking for that specific value. So we say some node, and then inside of this code block we're going to say let val equals node.floor.value. Okay, so now we're trying to get us that value that we're looking for, and we're going to match on that value. If that value exists and is valid, well, we don't want to do anything with that value. We just want to return that value. Otherwise, if that value does not exist, then we just want to return our key. And so now all we're trying to do is exhaust all of our match statements. So this none is matching this match statement. So we will say none some key. So now we're at our last. So instead of if it's not greater than or less than, we can be equal. So now we're trying to handle that, which in that case, if it's equal, then we would just return some key. Otherwise, now if nothing works, then we just return none. And this looks pretty good. So what are we doing here again? We're matching on our value with some key. We're comparing that key to the value. If it is greater than, then we want to go to the left to try to get that value that is the greatest value but less than our value, right? So if we pass in a 6 here, then it would be great if we had a value of like 5, right? Because it's the largest value we can have in the tree, smaller than 6. So that is what we're trying to do here in our floor. So if we're greater than, we go to the left. If we are less than, then we need to go to the right. Right? So if we're less than, so if we're 4, then we need to go to the right because we want to look for that 5 on the right. And then here we're trying to get that value. We want to match that value. If that value is valid and is good, then we return that value. Otherwise, we just return our key. And then we just start exhausting the rest of our match statements because Rust wants our match statements to be exhaustive. So all of this looks pretty good. Obviously, we need to test it out to ensure that it looks good. So here we're going to do our test, our searching. And we're going to say let tree equals create our tree. So we want to assert if our tree.search contains a reference to 5. And then we'll do a couple more just to make sure. So we want to see if 5 exists, if 7 exists, we'll see if 15 exists, and then we'll see if 2 exists. And since we expect 2 to not exist, we expect false to be returned here, so we want to make sure that that is what we're checking for. Our next test case is going to be testing our max and min methods. So we will let tree equals create tree, and then in here we will say assert equals, and we want tree dot maximum, unwrap it, and we want a 43, and we need to dereference this guy, and then we want to do the same for minimum, so we will change this to minimum, and our minimum value will be 0. And lastly, we have testing our floor. So test floor, and in here we will say let tree equals create tree, and then we will say assert equals dereference tree dot floor. We will pass in a reference to 42, unwrap the value that is returned, and if we pass in 42 in our tree, then we expect 34 to be returned. So that is why we put 34 here. So notice the value that we pass in does not have to be in the tree. So I did 42 to make sure that 34 is returned. So we don't have to see if, and we could do another floor just to verify. So we'll do floor and we'll do 30. And 30 we would expect 27 to be returned. So now if we run our test cases, we see that everything passes successfully. So it looks like all of our methods are running correctly, which is great. But now I have a little assignment for you. So there is, like maximum, minimum, there is a counterpart for ceiling, or for flooring, excuse me, and it is called seal. So we want to test floor and seal here. Test seal method. And for us to test seal method, we will say assert equals, and we will dereference our tree.seal, excuse me. And in here we will pass in 6. We will unwrap it, and if passing in 6, we expect 7 to be returned, right? So what is seal? Sealing is going to return the smallest value in the tree greater than the value we pass in. So we're passing in 6. So if we look at our tree, what is the smallest value greater than 6? It'll be 7. So that is why we want 7 returned. So if we did another value, we'll say we'll put in 40, then we would expect 43 to be returned here. So to set this up, because I want you to take this time after this lecture to try to implement in the seal method. So we will have our self, we will pass in our value, and we are going to return just like this. So for the assignment, I want you to implement in the seal method, and just as a hint, it will be similar to floor with minor tweaks to it. So think about what we did for max and min and how similar they were, and try to implement in the seal method. We will go over my solution to this assignment in the next lecture. And if you have any questions, please feel free to ask them in the Q&A section, and I will get back to you as quickly as I can.